Good afternoon, everyone. My name is Bumiller. I'm a rising senior at the University of South Carolina studying chemical engineering, and today I'm going to be speaking to you about the air pollution in Joshua Tree National Park. Joshua Tree National Park is located directly east of the Los Angeles Basin, as well as east of the San Bernardino Mountains to the north and the San Jacinto Mountains to the south. On a clear day, you're supposed to be able to see the Mexico border from Keys View, which is located within Joshua Tree National Park. But in 2017 so far, Joshua Tree has had 55 ozone exceedances of the EPA 8-hour max standard. The standard is set at 65 ppb, and so far, Joshua Tree has had a max of 98 ppb ozone. It is currently on track to have the most ozone exceedances this year, even though Sequoia had the most exceedances last year with about 90 days. Over the past 6 weeks, I've investigated why Joshua Tree's ozone pollution is so bad. There's no local sources within the park to cause this much ozone pollution, so I've looked at where this pollution could be originating from. It is a national park, it's protected land, so you think that it would be clean and pristine, but it really isn't, so I've investigated why. Before I begin, I just wanted to give an overview of the park itself. On July 15th, we went to Joshua Tree National Park and took multiple ground samples throughout the park. This map highlights multiple of these locations. So starting from the west, we have Black Rock. Moving east, Keys View, Wilson Canyon, Cottonwood, Oakdale Road, and Pinto Wells. Although we did not actually take a ground sample at Pinto Wells, there's a National Park Service meteorological station set up there, and I will be using data collected from that station as well. The main method of analysis that we used is gas chromatography. We injected our air samples into the system where it is split into 6 different gas chromatography columns. Attached to each column, there is a detector, and we used 3 different detectors. We used a flame ionization detector, an electron capture detector, and a mass spectrometer. Haberly will go into more detail on how these detectors measured different compounds and concentrations present in each sample. To begin, I looked at ozone concentrations over 3 days at 3 different locations within the park. This data was collected from meteorological stations set up throughout the park, and there is a consistent trend of Black Rock, the farthest west location, having the highest concentrations of ozone at around 4 or 5 o'clock each day. Pinto Wells, on the other hand, has the lowest concentrations of ozone each day. So what we're seeing here is that there's a pollution gradient from west to east developing throughout the park. Another way to look at this gradient is with the alkanes present in the atmosphere. Alkanes are precursors to ozone, so it's also important to look at these as well. Again, we see the gradient from west to east. Ethane, propane, N-butane, I-butane, and N-pentane are all decreasing as you move east across the park. Being in Joshua Tree all day on July 15th, we were able to capture a time series at 2 locations, Black Rock and Keys View. I chose to graph the alkanes and the alkyl-nitrates because before we even looked at this data, we were assuming that photolysis was converting alkanes to their subsequent alkyl-nitrates. If we look at the alkanes at both Black Rock and Keys View, we see a consistent trend of the concentrations decreasing in the afternoon. I've also added hydrofluorocarbon 152A to these graphs almost as an indicator that if diffusion is happening in the atmosphere. So if diffusion is happening in the atmosphere, HFC 152A will decrease in the afternoon because the boundary layer is increasing, so subsequent concentrations of all compounds will decrease. HFC 152A is non-volatile, so it shouldn't be reacting with anything in the atmosphere, which makes it a good indicator for diffusion. So if we look at Keys View, we see that in the afternoon, HFC 152A significantly decreases. Then if we look at the alkyl nitrates at Keys View, we see that for a majority of the time, including ethyl nitrate, propyl nitrate, and 3-pentyl nitrate, those concentrations still increase, indicating that photolysis is still prominently happening at this location. But if we look at Black Rock, it's a different story. HFC 152A is not decreasing in the afternoon. We would then assume that the alkyl nitrate concentrations should increase then in the afternoon. But this isn't necessarily happening either. They're actually decreasing for the most part. We can then assume that the photolysis is happening elsewhere, and then the alkyl nitrates are being blown into the park at different points throughout the day, affecting our measurements. So we're seeing different reactions happening in the atmosphere, and what I wanted to look at is which compounds are really causing the tropospheric ozone to be formed inside the park. So one way to do that is calculate the OH reactivity. The hydroxy radical is a key component in tropospheric ozone formation. So I was able to calculate the OH reactivity for each compound that we sampled for by taking the reactivity coefficient, then multiplying it by the concentration. Then I was able to calculate the total OH reactivity at each location by taking the reactivity of methane, carbon monoxide, and the VOCs and adding them together. It's interesting to point out that the VOC reactivity is higher than the methane and carbon monoxide reactivity added together for all locations. This is interesting just because methane is so prominent in the atmosphere. Moving forward, I'm going to look further into the VOC reactivity profile throughout the park. So as a park average, we see that oxygenates do dominate the reactivity in the atmosphere, but biogenics still hold a large portion of that reactivity with about 31%, which is huge. Moving on to a time series of black rock, we see that in the morning, biogenics hold the most reactivity with about 61%, and then increase to about 72% in the afternoon. Keys View is quite the opposite, with oxygenates having 55% of the reactivity and then increasing to 78% in the afternoon. But overall, with such a large biogenic source throughout the park, we can infer that the atmosphere above Joshua Tree is being affected by an agricultural source. Then HySPLIT back trajectories from Black Rock and Keys View both show that wind is coming from the Salton Sea agricultural area, coming up through the Coachella Valley, up and over the mountains, and starting to take that right hook into the park. This wind, as well as creating the biogenic source, is also then creating the west to east gradient across the park. Looking at the OH reactivity from west to east across the park, we see that that same gradient is starting to form, with Black Rock having the highest, then slowly decreasing to Wilson Canyon. But then Cottonwood and Oakdale have a spike. Looking at different HySPLIT trajectory models, Cottonwood also has a second wind source coming straight from the Salton Sea agricultural area. And instead of coming up through the Coachella Valley, it is going straight through Cottonwood, causing that spike. Then looking at isoprene concentrations, isoprene is a main biogenic that we tested for. We see that Black Rock again has the highest concentration, dropping off to Keys View, again dropping off to Wilson Canyon. Cottonwood again spikes in concentration, and we can attribute that to that same second wind source. So to conclude, there is a pollution gradient in Joshua Tree National Park forming from west to east due to those southerly winds from the Salton Sea agricultural area. By calculating the OH reactivity frequency, we see that VOCs do dominate the frequency of reaction with the hydroxy radical, and that oxygenates do count for 50% of the reactivity, but biogenics still have a large source, indicating that there is an agricultural influence on the atmosphere above Joshua Tree. HySPLIT trajectories confirm this hypothesis. Future work would include flying over Joshua Tree from west to east on that latitudinal line to see if we can capture that gradient with flight data, as well as taking more ground cans throughout Joshua Tree National Park. Hopefully, within the same research flight, we could fly directly over the Salton Sea agricultural area to be able to compare directly that data to Joshua Tree. And as well as being able to compare Salton Sea agricultural area to Joshua Tree, we can see how the pollution is evolving next year, if it's getting worse or if it's getting better. I'd like to thank Don Blake, Stacy Hughes, and Sam for all of their help and support throughout this process, Emily Schaller and Melissa Yang and NSERC for making this program what it is and for this opportunity. I'd like to thank the Roland Blake Lab for their hospitality and all help analyzing our air samples, as well as the flight crews for giving us safe and as least bumpy flights as possible, as well as the WAS group for all the motivation and support throughout the summer. Thank you.